The discussion that will follow is very important. You must acquire a good understanding of the concepts that will be covered next so that you can successfully tackle the next sections related to steam consumption, steam piping and equipment sizing, steam distribution, and condensate recovery, just to name a few. So please take the time to watch this video carefully. If in doubt, please feel free to ask us for help in the Q&A section or drop us an email at contact@wrtraining.org. Okay, now to begin our discussion, please keep in mind the 5 main most commonly related terms associated with the subject of heat transfer are heat flow rate, thermal conductivity, thermal resistivity, thermal resistance, and thermal transmittance. In this section, we will describe each one of them and how they are related to each other. The traditional method for calculating heat transfer across a plane wall considers the use of an overall heat transfer coefficient, or more correctly, the overall thermal transmittance between one side of the wall and the other. U values are quoted for a wide-ranging combination of materials and fluids, and are usually influenced by empirical data and operating experience. The previously mentioned films of condensate, air, scale, and product either side of the metal wall can have a significant effect on the overall thermal transmittance, and because of this, it is worth considering the whole issue of heat transfer across a simple plane wall and then a multi-layer barrier. So let's start with a simple plane wall. A good way to start is by looking at the simplest possible case: a metal wall with uniform thermal properties and specified surface temperatures. In this example, T1 and T2 are the surface temperatures either side of the metal wall, and the temperature difference between the two surfaces is delta T, as seen here. Ignoring the possible resistance to heat flow at the two surfaces, the heat flow rate through the wall can be expressed as follows, where Q is the heat transferred per unit time. Small k is the thermal conductivity of the barrier. A is the heat transfer area, delta T the temperature difference across the barrier, and X the thickness of the barrier. Note here that the term barrier refers to a heat-resistive film, or the metal wall of a heat exchanger. It is possible to rearrange this equation into the following equation. It can be seen from their definitions that the ratio X to K is the thickness of the barrier divided by its inherent property of thermal conductivity. Simple arithmetic dictates that if the length of the barrier increases, the value X divided by K will increase, and if the value of the barrier conductivity increases, then the value of X over K will decrease. A characteristic that would behave in this fashion is that of thermal resistance. If the length of the barrier increases, the resistance to heat flow increases, and if the conductivity of the barrier material increases, the resistance to heat flow decreases. It can be concluded that the term X divided by K relates to the thermal resistance of a barrier of known length. Now, the results of simple electrical theory parallel the equations pertaining to heat flow. In particular, the concept of adding resistances in series is possible. and is a useful tool when analyzing heat transfer through a multi-layer barrier, as will be seen in a later video. Now, this equation can now be restated in terms of thermal resistance as follows, where the resistance R equals the ratio of the thickness to conductivity. This is termed the thermal resistance of the barrier. Thermal resistance denotes a characteristic of a particular barrier and will change in accordance to its thickness and conductivity. In contrast, the barrier's ability to resist heat flow does not change, as this is a physical property of the barrier material. This property is called thermal resistivity. It is the inverse of thermal conductivity and is expressed as follows. Now, the question is, how can we relate the overall resistance to the overall heat transfer coefficient? The usual problem that has to be solved in heat transfer applications is the rate of heat transfer, and this can be seen from the general heat transfer formula already discussed in a previous video. Here, U is the overall heat transfer coefficient, or the overall thermal transmittance. By comparing the two equations displayed now on screen, it can be seen that U equals 1 divided by R. Thus, the U value, so the thermal transmittance value, is the inverse of resistance. Okay.